everyone. Welcome to the One World Combinatorics Onwards seminar. Our speaker today is Hajime Kaneko from the University of Tsukuba, and he is going to speak to us about analogs of Markoff and Lagrange spectra on one-sided shift spaces.
Thank you for introduction. Today, I would like to talk about the in some sense analogy of classical Markov and Lagrange spectra. It's related to, so original Markov and Lagrange spectra is related to rational approximations of badly approximable numbers. In later, multiplicative version of Markov and Lagrange spectra was discovered. And in point of, so in the theory of it, so combinatoric theory is important. So in point of combinatorial part, so I and Professor Wolfgang Steiner consider analogy for Markov and Lagrange spectra on one-sided shifted spaces. So today I would like to talk three topics. First is motivation. Because I'm a number theorist, so I would like to talk about the motivation from Diophantine approximation problems. However, there exist many problems of Diophantine approximations, but because of time, I would like to talk only simple case. In the next section, section 2, can you see this red line?
Yes.
So, in the next, I would like to talk the in some sense generalization for shift of spaces with general order. In the section 1, I would like to talk only lexicographical order. And for considering the original motivations, so we need to consider symmetric alphabets. So anyway, I would like to talk from the beginning, the motivation of it. So the Diophantine approximation problems. It's Diophantine approximation problems related to geometric progressions. It's uniform distribution theory. And the classical results by Weil, 1916, means for any real number alpha greater than 1, this is a common ratio. And for almost every real number Cauchy in the sense of Lebesgue measure, so the geometric progression C alpha to the n is uniform distributed modulo 1. I'm sorry, I omit the details of the definition of uniform distributed modulo 1, but it's related to the fractional parts of geometric progressions of this. In particular, in the case where alpha is integer greater than or equal to 2, then so this sequence is uniformly distributed modulo 1 if and only if C is normal number in base B. However, you know that for example, for individual C, it's generally difficult to answer whether C b to the n is uniformly distributed modulo 1 or not. So that means it's difficult for individual C that it's difficult to determine whether C is normal in base B or not. For example, square root 2 is normal in base 2. This is a famous Borel conjecture. And what I want to say is that this problem is related to base B expansions of C. That means So you know that base B expansion is related to word combinatorics. And the target of, so uniform distribution is a difficult problem. Today, I would like to talk about the partial results. So lim sup of this one. Here, this symbol means the x is a real number. This symbol is so the distance from x to the nearest integers. For example, in the case where x is 5.9, the nearest integer from 5.9 is 6, and the distance is minus 0.1. So if Cuc bit to the n is uniformly distributed modulo 1, then this value is 1 over half. So today, our target is the set of, so this is maximal limit point of the distance. In some, so I don't tell the detail, but this set LB has analogous properties of classical Lagrange and Markov spectrum. So in the next slide. And in particular, I would like to talk about the analogy of discrete part. So this is the set of maximal limit point of so geometric progressions where common ratio is fixed, and so this Cuc moves. And the next theorem is that in some sense, discrete analogy of discrete part of classical Markov and Lagrange spectrum so occurs. That means so there exists a CB in this set satisfying the following. We consider the point of this LB, which is less than this value. Then it's written like this. So the minimal point and the second point and the third point. And this tends to CB. That means CB is the minimal limit point of this set. In the classical Lagrange, so I don't tell the definition of a classical Lagrange spectrum, but discrete part of classical Lagrange spectrum tends to 3. So this CB is analogy of the 3. And so interesting point is that below this CB, it's a rational number, and the minimal limit point is a transcendental number. And we call this part the discrete part of LB. So I wanted to talk about this set because the base B expansions of these numbers are related to substitutions. So substitutions is related to word combinatorics. So I would like to talk the details for the next slide. And this is the set, and this discrete part, and CB is the minimal limit point. And we define the substitution tau from 0, 1 to 0, 1. So 0 is sent to 1, and 1 is sent to 1, 0, 0. So I would like to introduce some words related to these substitutions. Initial word is A0 is 0, and AM plus 1 is defined by this substitution and of AM. For example, A1 is tau of 0. That means A1. And next, tau of 1 is 100. And A3 is tau of 100 is 10011, and so on. You know that this converges because AM is a prefix of AM plus 1. So this sequence converges to certain infinite sequences. And this is a fixed point of this tau. And using these words and sequences, we can denote the base B expansions of this and this CB. And in order to explain that, so we need to introduce certain function phi for any so sequence x, so x0, x1, and so on is 0 or 1. We put phi x by 1x0, 1 over x1, 1x0 to x. So 1 over 1 over, and the middle part is x 0 to x0, 0 to x1, 0 to x2, 0 to x3. Here, 1 over means -1. So the meaning of this is the following. If xn is 1, then we insert 0. And if xn is 0, then 0xn is empty word. So we consider examples. And so, for example, we consider phi of AM infinite. That means phi of AM, because A to infinite is 100, 100, 100. So this one corresponds to the inserting of 0. Is it clear? Is it okay? And so Vi infinite is the image of A infinite. And the base B expansions of this DB and this CB is written as follows. So the base B expansions of this DBM is written in terms of this VM. And the base B expansions of this CB is denoted by this V infinite. And so the next one is example by V2. So DB2 is here. This is written by this V2. And this is base B expansions. And 1 ver corresponds to -1. So, and the third one is written like this. It's a rational number because this part is periodic. So this result is essentially by Daviscus in 2006. So what I want to say is that so this problem is totally defining problem, but the results comes from word combinatorics or the substitution. So my motivation is, so I would like to discover the mechanism why substitution appears here. So in order to explain that, so I would like to introduce examples of lemma sup of C to the B to the N. And for simplicity, we consider the case where B is at least 3. So we consider the case where C is a particular real number, like this. So sigma of B to the -m squared. So here 1, and this is 4, and this is 9. So the base B expansion is like this. And so because B is at least 3, it's less than 1/2, and it's the distance from this is C minus 0 is the distance of nearest integers. And we consider Xc and Xb. You know that the base B expansion of Xb is written by the shift. If so, we multiply B, then the sequence shifts like this. And if we consider the fractional parts as the distance, we omit this 1. So it's the shift. In the case of C B to the 2, it's the same, 2 shifts. So this is 2 shifts. So key observation is that the distribution of the first is the corresponds to the shift of these words. And considering the lemma sub, then it corresponds to so 1 0 0 0 0, because you know that so this gap goes to infinity because the gap is written by m plus 1 square and minus m square. This tends to infinite. So the sub word is written as 1 0 infinite. So this can be interrupted in terms of a sequence. And we consider sequence corresponds to the base B expansions of C. Here, this. And the lemma sub word, so with respect to lexicographical order, is 1 0 0. That means so 1 0 infinite. So we consider lexicographical order because you know that so 2 base B expansion is so the order of base B expansion corresponds to the lexicographical order in this of sequences. So for this problem of this type of Diophantine problem, we consider lemma sub words related to lexicographical order. And so, by the way, sub of this one is this. So I would like to introduce this later. But our goal is, at first, our goal is lemma sub words with respect to one-sided spaces. So here we consider lexicographical order, but for further application, we need to consider one-sided spaces with general order. So in what follows, I would like to consider general order, and we research minimal limit point in terms of substitution. And that means I would like to consider analogy of this CD. So in what follows, so I would like to move on the next section. Is it okay? In what follows, I would like to talk about the Markoff-Lagrange spectrum of one-sided sequences. So now I would like to introduce a certain order on 0, 1 infinite. Here, the alpha rate is 0, 1, and a to the infinity is the sequence. So one-sided sequence, the A1, A2, and so on is 0 or 1. You know that this set has a distance like this. So this is a two different sequence. It's a natural distance as 2 to the minus k, where k is the minimal index, such that these are different. And its natural definition, so A1 and AM are 0 or 1, and A1, AM is a cylinder set. That means this is the set of sequences A1 prime, A2 prime, and so on, so that the first k letters coincide with this A1 and AK. So we introduce cylinder order on this set. So, and cylinder order on -1, 0, 1 is also defined. And I would like to use the cylinder order on this set in the next section. And so this is a total order on A infinite. And so this is a cylinder order if and only if the following holds. And B, C are sequences, and so A and B, A is less than equal to B and less than equal to C. And this implies the distance of A and B is less than equal to distance of A and C. So maybe it's not so clear, but so I would like to introduce equivalent definition of a cylinder order. And let k be a positive integer, and A1 and AK is a word of length k, and B1 and BK is a word of length k. So we define this cylinder set is less than this cylinder set if and only if for any A and B, so A from this cylinder and B from this cylinder. So this equality holds. That means any element of this one is less than any element of this one. And total order on this sequence, this set is cylinder order if and only if for any positive k. So this one is total order on the set of cylinder set of length k. So I would like to talk the examples in the next page. So most easiest cases is lexicographical order. I would like to talk about the lexicographical order. So this A and B are two sequences, A1, A2, and B1, B2, and so on is 0, 1, 1. And let M be the minimal index such that these are different. You know that the lexicographical order is defined as follows. A is less than B if and only if. So AM is less than BM. M is the minimal index. So you know that by this definition, 0 is the cylinder 0 is less than the cylinder 1. That means any element from cylinder 0 is less than any element of cylinder 1. And in the case of length 2, so for example, any element from 1, 0 is less than any element of 1, 1. Of course, 1, 0 something is less than 1, 1, and so on. So it's the image of a cylinder order. For any cylinder, so this order is well defined. The next one is alternating lexicographical order. And we define this order by this. If this value is odd, like M is 1, it's the usual order. And if M is even, we consider inverse order. If so if AM is greater than BM, then A is less than B. And so this its length 1 is the usual order. And its length 2, we need to consider inverse order. 1 is less than 0. 1 is less than 0. So this in this case, 0 and 1 appears the order part is the usual order. 0 is less than 1. And in the case of length 3, it's odd number is the usual order. And for example, 1, 0, 0, 1 is less than 1, 0, 0. Because this is even. And we define lemma subwords and subwords like this. So let A be a sequence from 0 and 1. So we write the lemma subwords. So lemma sub of shift words, we write like this, L, L. We write the subwords relating to shift by S. For example, so this is a review. We consider lexicographical order. And AN is 1 if and only if N is square 1, 4, 9, 16 or something. So it's a review. So lemma subword is 1, 0, 0, 0, and it's 1, 0 infinite. And it's easily seen that the subword is A itself, because you know that subword comes from this 1, but here the gap is the gap is the smallest at this point. So the gap is 2, and the gap is 4, and the gap is maybe 6. So gap is strictly increasing. This is the smallest gap. So the subword is A itself. So in the next slide, I would like to define the analogy of Lagrange spectrum and the Markov spectrum with respect to this order. This order is the cylinder order. So this property is important. And so this L is lemma subword, and this S is subword. And so this L is the set of lemma subwords, and this M is the set of subwords. In the classical theory, so this one is related, so corresponds to Lagrange spectrum, because in the classical theory, and so Lagrange spectrum is related to lemma sub of continued fractions, and in the classical theory, and Markov spectrum is related to the sub of continued fraction. This is a natural analogy. And the interesting point is that so Professor Wolfgang Steiner proved the following incredible property. So in the classical theory, so Lagrange spectrum and Markov spectrum are different. But in this setting, the Lagrange spectrum and Markov spectrum is the same. So it's an incredible property. And so in the classical case, Markov spectrum is larger than Lagrange spectrum, but in this theory, these are the same. and it's a closure of a subword of purely periodic. And here, closure means so it comes from the fact that A finite is a metric space with this metric. So it's okay. So the next, I would like to talk about the minimal limit point of these two sets. So definition of L and M and are written in this, but because these are the same, I only write the definition of S. So L and M is this set, and this is the cylinder order. So in what follows, I would like to discuss the analogy of discrete part. So rewrite M, the minimal limit point of these two sets. So the point below of the minimal limit point and the point below this point is written in terms of substitutions. So you know that here we wrote the discrete part by substitutions. So we need to generalize this tau. So let J and K are integers, which are non-negative, and K is greater than J. Tau JK is a substitution, and the tau JK, so 0 corresponds to 1, 0 to the J, and 1 is tended to 1, 0 to the K. In the case where tau 0, 2 and 1 to 0 to 0 is 1, that may correspond to this tau 0. And tau 0, 2, 1 is 1 to 0 to 2, as it corresponds to this. So the result of the viscous corresponds to tau 0, 2. And we consider the set of this tau jk. In some sense, we need to consider S-adic systems. In some sense, generalized S-adic systems. We consider the sequence of substitutions. And we consider, so this means the composition, iteration. And this sigma means the limit. We can show that this always converges, like this. Oh, no. Like this. So this always converges. Here, next page, we describe the discrete part in terms of this notation. So for simplicity, we assume that the cylinder 0 is less than 1, because if 1 is less than 0, we can change 1 to 0 and 0 to 1. So we may assume this inequality. And so this is the notation from the previous pages. So discrete part has two cases. So exactly one of the following holds. So at first, this is minimal limit point. So minimal limit point is written in terms of S-adic systems. And moreover, the discrete part is written in the partial iteration, and we consider periodic one. Here, in the case where n is 0, this means 0 to the infinite. And in some sense, in the second case, and the substitution appears only, so there exist only finitely many substitutions. And the minimal limit point is written in terms of finite substitutions of this one. And here, if h is 0, this implies 0, 1, 0 infinite. And so discrete part is also defined by, written in terms of this sigma 1 and sigma h. Here, sigma 1 to the sigma n, where n is less than or equal to h. And this part is written in terms of this sigma 1h. So anyway, I would like to introduce the examples in the next slide. So in the next, here, I'll only introduce examples related to the first case. So I omit the second statement. This is the same as the first statement of the previous page. We consider the case where this cylinder order is alternating lexicographical order. So this is the definition of alternating lexicographical order. In this, so we have an algorithm to determine this sigma 1, sigma 2, and so on. So using this algorithm, we can prove that for any n, sigma n is tau 01. This is tau, and so sigma 1n corresponds to nth iteration of tau, and the minimal limit point is the limit of this one. And so it is easily shown that this one is equal to this. So it's in some sense, this theorem is generalization of the result of the Professor Dubitskas. And so I omit the details, but we can apply this result to unimodal order. Unimodal order is here. This is two sequence, and this is the minimal index such that so AN and BN are different. And we consider the number of 1 below this M. And so A is less than B if and only if. So it depends on the number of this M. So this corresponds to the dynamics of unimodal maps. So like tensor map. So this 0, 1, so this part it corresponds to 0, and this part corresponds to 1. And if we take 1, then the slope is negative. So order is inverse if this 1 appears. Even in this case, we can determine minimal limit points in terms of this tau jk. I'm sorry, but because of time, I'll omit the detail. But so sigma 1 is tau 0, 1, and sigma for any n greater than or equal to 2. So sigma n is tau 0, 2. It's determined by algorithm. So anyway, what I want to say is that this theorem is flexible, and it can be applied for any cylinder orders. So in what follows, I would like to move on the last section. Is it okay? I have 8 minutes. Is it right?
Yes.
Okay, thank you. So because of the original motivation comes from this, and here when an is -1 or 0 or 1, and more generally we consider general version. For example, we consider my negative beta expansions and the general and the signature. So we consider general order related to this problem. Because the motivation is absolute value, we consider absolute values of sequences. So A comes from -1 or 0 or 1. So absolute value of A is A if the A is lexicographically greater than or equal to 0 infinite. And absolute value is -A if A is lexicographically less than or equal to 0 infinite. So because of this motivation, we consider simpler case. So cylinder order is consistent if and only if the following holds. And for any omega, so W finite word, so this order holds or this order holds. So it comes from this motivation. You know that, for example, so in this setting, so 0, 1 is greater than 0, 0, and greater than 0, 1 bar. So it's a natural assumption comes from this setting. So we also consider absolute value version of limit subword and absolute value version of subwords, and absolute value version of Lagrange spectrum and absolute value version of Markov spectrum. And the next theorem is that even in the case of absolute value version, so these two sets are same. Here, B to infinite is also a metric space. So closure means comes from this metric. So it's a closure of subwords of purely periodic ones. And the next target is the minimal limit point of this set in some sense, it comes from the original problem of Professor Davidskas here. So this is the minimal limit point of Lagrange spectrum, and for simplicity, we consider the case where for simplicity we assume the following two inequalities. It's just for simplicity. So we recall that for any sequence x0, x1, and it's from 0, 1, infinite. So phi x is defined by this. And so for general cylinder order, so this is a consistent cylinder order. And the conclusion is that so this minimal limit point of this set is written in terms of the map of M. So this M. So this M is in some sense minimal limit point of 0, 1 case. So this one is a certain cylinder order on the set of 0, 1. And the discrete part is also denoted in terms of cylinder order on this 0, 1 infinite. And we have algorithm to determine this cylinder order on 0, 1 infinite. And so I have 2 minutes. So I would like to explain the examples of this theorem. So in the case where, so this one is original lexicographical order. So by this algorithm, we can show that so this order on 0, 1 infinite is alternative lexicographical order. And the minimal limit point is the map of minimal limit point related to alternative lexicographical order. So, and this value is written in terms of limit of tau 0 to n. This is here. So this is here. In some sense, so in this meaning, so this theorem is a generalization of Professor Davidskas 2006. And I'm sorry, but we have more applications for alternative lexicographical order on the -1, 0, 1 and bimodal order on -1, 0, 1 infinite. But so I'm sorry, but I omit the details. But so this generalization has other applications. So it's the time. So thank you for your listening.
Oh, thank you very much, Hajime. Does anyone have any questions? Does it make sense to consider larger alphabets?
It's nice questions. Next, it's next target.
Okay.
And of course, so if you know the original Lagrange spectrum, so original Lagrange spectrum comes from both-sided sequences. So I think it's interesting to consider both-sided version of our research.
Right. Okay, thank you. Does anyone else have any question? All right. If not, thank you again, Hajime.